This is the second part of the notes for specific heat, or notes 5. This can be found on page 20 of your packet if you're following along. So on this page, we have an example problem about an aluminum block with a mass of 0.25 kilograms, initially having a temperature of 100 degrees Celsius, and being placed into water, where then the final temperature of both the water and the aluminum block becomes 50 degrees Celsius. And it tells us the specific heat of both of these materials. So first part of this question says draw an arrow showing the direction of heat flow. In the problem, it tells us that the aluminum block starts at a temperature of 100 degrees Celsius and then ends at a temperature of 50 degrees Celsius, because both the water and the aluminum do that. And so I'm going to start to draw a temperature diagram over here with 100 degrees Celsius being the starting temperature, and then showing that the aluminum drops in temperature down to 50. And I'll just label this to show we're talking about aluminum. Because the temperature of the aluminum drops, that means that heat must have been leaving it, because the average kinetic energy of the particles in the aluminum block lowered, and so it lost energy. So in part A, I'm going to draw arrows out of the aluminum block into the water, because that's the direction that the heat flowed. Then we can start filling in the values from the problem. So you'll notice that we have mass, specific heat, and change in temperature, and all of these have the subscript Al for aluminum, and then all of these have the subscript water for water. So the mass of the aluminum is 0.25 kilograms. The specific heat of the aluminum we can find at the end of the problem. It is 900, and then the units are pretty weird. It's joules per kilogram degrees Celsius. The change in temperature of the aluminum, we're going to use this temperature diagram, because the change in temperature is shown by going from 100 down to 50. So we can find the change by subtracting these two numbers and finding the difference, which is 50 degrees Celsius. So notice that we're not just taking this number. We're not doing that. What we're doing is we're finding the difference in temperatures from the aluminum at the beginning of the problem and the end of the problem, and it dropped 50 degrees Celsius. Then the mass of the water is 2 kilograms, and the specific heat of water is 4,184 joules per kilogram degrees Celsius. We don't know the temperature of the water, or the change in temperature of the water, because we don't know what temperature the water started at, and that's what we're going to solve for. For part C, it says the heat lost by the aluminum is equal to the heat gained by the water, so the Q or heat of aluminum is equal to the Q or heat of water. Rewrite this equation using the formulas, and so this is the formula that we learned yesterday. And so in order to make sure that we're organized, I'm going to add a subscript Al to all of these variables on the left side of the equation, and then I'll add the subscript water to all three variables again on the right side of the equation, so that we can stay organized. So you can see that we've got the mass of the aluminum times the specific heat of the aluminum times the change in temperature of the aluminum. That's all on the left side of the equation, and then is equal to those same three variables, but only pertaining to water on the right. So at this point now, we have 6 distinct spots that we can start to plug values into and substitute. And so that's what I'm going to do for part D. I'm going to write down the mass of the aluminum, and the specific heat, and so on. Now you'll notice here that we don't have the change in temperature, and so I'm going to leave that of the water as a variable so that we can solve for it. And now what I'll do is I'll multiply all of the numbers on the left side to find the heat lost by the aluminum. And then I'll multiply just the two numbers that we know about the water so that we have a more simplistic algebra problem in order to solve for this unknown variable. So on my calculator, I'll do 0.25 times 900 times 50, and that gets us 11,250 joules is equal to 2 times 4,184. So that's 8,368 times the change in temperature of the water. So now I can divide both sides by this 8,368 to cancel it out. And then we'll get the change in temperature of the water (8,368). The change in temperature of the water is 1.34 degrees Celsius. So now we have to ask ourselves, did the temperature of the water increase or decrease? And that will be easier to answer if we look back up at our temperature diagram. So our temperature diagram is over here. It shows that the aluminum went down in temperature. Because of the way that heat transfer works, this ending temperature that both the water and the aluminum ended at has to be between the starting temperatures of both. And so I'm going to draw another arrow that shows the temperature or the change in temperature of the water. And so we can see that the water must have started at some number below 50 in order to meet in the middle at 50 degrees Celsius when the aluminum was added to it. And so based on this diagram, we see that the water rose in temperature, so it increased. And so then all of our math told us that the change in temperature of the water was 1.34 degrees Celsius, and we need to figure out where did the temperature start so that after we added 1.34 degrees Celsius, we ended at 50. And so the last question asks, what was the initial temperature of the water? And so we need to find what is a temperature that is 1.34 degrees Celsius below 50. And we will get 48.66 degrees Celsius, which is what the temperature of the water was before we added the aluminum. Thank you for watching.